Hello, fully remote students, and welcome to the Force of Kinetic Friction pre-lab. So in this lab, what we're going to do is to kind of break the force of kinetic friction, right? The force that resists motion because objects or surfaces are sliding or rubbing against one another, right? Down a little bit. We're going to break it down into something more fundamental. This is similar to what we did with the force of gravity. Right? At first, we just knew the force of gravity as an interaction between the Earth and the object. But eventually, we found out that the force of gravity could be calculated by taking the mass of the object and multiplying it by the local gravitational field strength, or F of g equals mg. We're going to get a similar thing here for the force of kinetic friction. A little different, more difficult to deal with, though, because friction is just a difficult animal to do, but we're going to use a nice pivot interactive here to look at, which I'm going to go over in a moment here. So, what factors might affect how much friction there is between two surfaces that are rubbing against one another? Well, oftentimes when I ask this question in class, somebody will say, well, what about the mass of the object? And I'll say, why mass? They'll say, well, because it's about the surfaces, getting pressed together. Because then gravity's going to pull it down onto the surface. Yeah, but what's gravity an interaction between? Well, it's an interaction between the entire Earth and the object. Is there a force that we've used that's due to the interaction between the surface and the object? Sure, right? If it's sliding over a surface, that force is the support force, or the normal force. Right? So we like to think of the force of friction being dependent on the size of the normal force. Now that's often related to the force of gravity in sometimes simple, sometimes more complex ways, but the normal force is proper because, again, it's the force between the surface and the object, which is where friction is. The other one that most people come up with is the types of surfaces. I think we just know from general experience that some surfaces are rougher than other surfaces. Now, there are other things we could throw in here, but we're not going to be able to test them in this lab, so we're going to kind of keep them on the outside and focus on these variables: force of friction, normal force, and types of surfaces. Now, because this is a fairly complex thing to try to measure, we're going to have to run some fairly complex equipment. Now, this is actually a diagram of what it's going to look like in class. It's similar to what you're going to see in your pivot, though, so I'm just going to use this for now, and then I'll show you what your pivot looks like so that you can kind of see the difference, but it's very close. So in class, they're using our little constant velocity cars we used back in the toy car lab, right, which move at constant velocity, on top of which they're putting one of our other carts, our fancy Bluetooth carts that have a force probe in there. And that force probe will be tied with a string, okay, to some what are called friction trays. Okay? You can put little masses. You can take the top one off, put some masses inside of it, change the mass of this if you wish. And when you run it, when you flip the switch, it's going to pull the trays at constant velocity, which means no acceleration. Okay? And of course, when something moves with no acceleration, what has to be true of the forces? They have to balance. Okay? That's going to be very important to understanding how we are going to figure out what the normal force and the force of friction is. Now, in your pivot experiment, as I'll show you momentarily, you just have a slab of wood instead of the friction trays. But they are attached to just a force probe, which is going to get pulled by hand at constant velocity. Not quite as high-tech as they're using in class, but it still works. Okay, the force probe, again, is attached to the slab of wood, and you can put masses on top of the slab of wood like you can put masses in the friction trays. But in either case, they're going to get pulled at constant velocity. So no acceleration, so balanced forces. So let's talk about the forces on the friction tray. Of course, there's a force of gravity between the Earth and the trays acting downward. And they are going to be on a track. In your case, I think it's wood on wood. And so that's going to support the wood block. And so there is a normal force acting up. And again, no acceleration, so those two forces have to balance. So if I want to know how much normal force there is between the track and your block of wood, right, I just need to figure out how much that block of wood weighs. And again, we know how to do that. It's mg. the mass of the block in kilograms times the local gravitational field strength, which we know from earlier in the year is our old friend 9.8 newtons per kilogram. Right? Since the units are newtons per kilogram, we have to have our mass in kilograms. Okay? Got to convert everything. In the actual video, it's all in grams, but I've helped you by converting that over already in your lab sheet into kilograms. Okay? So that's how we'll figure out what the normal force is, not directly, but by creating a situation where it is equivalent to the force of gravity, and then we can calculate the force of gravity. Now, there's a string here, so there's a force of tension. I suppose in your pivot it's an applied force, but there's still a force that's pulling the block of wood forward. And then, of course, there's friction between the wood and the table or whatever it's being pulled across, and that force will oppose motion, and so that's our force of kinetic friction. Remember, kinetic means moving, right? This is when the surfaces are sliding over one another, as opposed to static friction, when you might be pulling on something but it doesn't move because friction is keeping it from moving, right? So kinetic, static. Kinetic means motion, remember. And again, because it's not accelerating when it moves, these forces have to be equal. So if I want to know how big the force of kinetic friction is, I just need to know how big this tension or applied force is, which I'll know because it's attached to a force probe. And the force probe will tell us what this force is. So this is kind of an interesting lab where we're not actually measuring our variables directly, but we've set up a clever situation and high-tech equipment where we can actually see what those are, we can infer what they are because of the situation, because this is not accelerating. If it was accelerating, we could still do the problem, but we'd have to know the acceleration, and we'd have to do a complex Newton's second law analysis. So it's a lot easier if you just pull or move it at constant velocity. Now, for types of surfaces, you guys don't have to worry about this. In class, they're going to do half of the groups are going to do a tray that has cork on the bottom. So they'll be pulling cork across the track. The other half of the class is going to use a tray that has plastic on the bottom. And then in the post lab, we're going to look at what does that affect. Okay? I don't want you guys to have to do twice as much work, so you're just going to do the one thing, see your relationship and your graph and all of that. And then, just like everybody else does, right, you're only doing one surface, but then you can look and see what the other surfaces did to the results. Okay? So here is your pivot. Okay, this is a little movie of part of your pivot. This is a long video which shows, I think, like 7 different trials. So notice in each case, here's our block of wood. It's 223.3 grams, which is 0.2233 kilograms. You gotta move the decimal point here 3 places to get to kilograms. And then here's the force probe, and you'll see how they're attached together. So they're going to, when they hit start, they're going to lift the force probe up, and they're going to slide this across the table here, across the bigger wood, at constant velocity. And the little thing up here is reading the force probe. It's not Bluetooth like ours is, not quite as fancy, but it's going to read the force as a function of time. This is a force time graph. Now, you might say, man, that's really small, and it is, but if you blow up the screen over here, right, that'll make it bigger. Plus, you'll see at the end of the trial, they focus in on it, right, before they go to the next trial. So let me show you what it looks like here. Okay, so here they go. Right, they're going to pull this at constant velocity across the table as close as they can. And then they're going to zoom in on this. Okay? Now, you will notice some distinct parts to this. Okay, first off, notice the scaling. All right, this is -1 Newton, so this must be 0, 1, 2, 3, 4. That's a pretty simple scaling, but one thing you've got to be really careful of with this is that the scaling on this changes depending on the trial. So sometimes every line is worth a Newton, sometimes every line's worth 2 or 3, or I believe at the end there might even be one where it's like 5 Newtons for each one. Right? And so you just kind of have to deal with that. So make sure that you're careful that you're every time that you're looking at the scaling here. Okay? Now notice it starts out, I don't know why it's a little below 0. It's a little worrisome in their zeroing, but oh well. This essentially is 0, right? Because what they had done is they had hit collect here, right? But they hadn't started pulling yet. Okay? But then what's going on here? This was created while they were pulling. If you watch again, this is when they were pulling, but they weren't getting it moving yet. So this is actually static friction. Right? That was opposing the attempted motion. And notice it's got a range of values. It goes anywhere from 0 up to this spike here, this maximum. So this spike is what we call the maximum amount of static friction. That's how hard you have to pull just to get it going. Okay? If you pull any less than that, it doesn't move anything. Right? And there is a balanced amount of static friction canceling out your pull. But once you pull more than the maximum, it starts to move. And you'll notice that after it starts to move, it's essentially a horizontal line, right? Now, it's not perfectly horizontal. There's some error here. The biggest part of the error is what's going on kind of microscopically. Something's happening called slipstick, where the block of wood is alternately slipping and sticking to the piece of wood below it. So you got to pull a little harder when it's sticking and not as hard when it's slipping. And so that makes it bounce up and down a little bit. Okay? In class, they're selecting this horizontal part and taking an average, and I really wish they would have done that here, but they didn't. So what they want you to do instead is you have to estimate, pick a point in here, the horizontal part, all right? Not after when it stops, not before it gets moving, right? But this part, and then you've got to estimate the force of friction. So again, this is where the scaling is super important, right? Which is going to be different in different trials. So if this is 0, 1, 2, it's obviously more than 1 and less than 2. Well, we don't want to say just 1 or 2. That's going to be way off, so we got to estimate. So I'm picking in about here, I figure, is about the average. And that, to me, is a little less than a half, right? So I might say this is 1.3 or 1.4. Now, it is an estimate, so there's going to be some error there, right? Like I said, I wish they would do what we're going to do in class, which is select this part and then tell the computer to find the average. Right? Then we can kind of average out all these points, but you guys are going to have to just estimate. Sometimes it's fairly easy. Sometimes you have to work at it a little bit. If you get wonky data and you get a point that doesn't seem to fit, right, or your data doesn't give you the slope that you need to answer the question on the pivot, then the very last question on the pivot, right, then you might need to come back and look at this again. Okay? So you just estimate what it is, being very careful with the scaling. Right? And then you'll notice that what it does is that after it blows it up, you can pause it like I did. The next trial, then, you'll notice they've added masses. How much mass? It tells you right up here. It's added 200 grams, which is 0.200 kilograms, to the 223.3 grams for a total of 423.3, which would be 0.4233 kilograms. Right? And I've helped you out with that on the sheet, right, on the lab sheet. And then it's going to pull it again, and it's going to zoom in again. And every time, it adds another 200 grams, all right, to the block. So you'll see on your lab sheet, if you print that off there, right, that I've tried to help you by writing out the masses. Now remember, the normal force is not the mass. The normal force in this case is equal to the weight of those masses. So you got to calculate the normal force by doing mg, and m has to be in kilograms. G is 9.8 newtons per kilogram. Force of kinetic friction, you pull off the graph, and you estimate. Okay? So, the normal force we can control, right? And we can control it by how much mass we pile up here onto this thing. We change the mass that we're pulling, we've changed the force of gravity, we've changed the normal force. So that makes the normal force an independent variable, one that we can control. And like I said to you, you're going to start out by doing a trial with just the block of wood, 0.2233 kilograms, and then you're going to add 200 grams or 0.2 kilograms every single time, right, and run it. Your force of friction will be our dependent variable, so when you're making a graph, it's going to be force of friction versus normal force. Force of friction on the vertical axis, normal force on the horizontal axis. Got to get them on the right axis, or you're inverting your slope. Let's see. Types of surfaces, remember, we're looking at in class, and you'll see that in the post lab. So again, this is kind of like more like what they'll see in class, right? And they will take an average of these. You just have to estimate, okay? This is before it starts to pull. This is the static friction. That's the maximum amount of static friction it has to overcome. That's kind of an important thing, right? Is how much do you have to pull to even get it going? And then this is the kinetic friction, right? I do want you to notice, though, then in every one of your trials, the kinetic friction is less than the maximum amount of static friction. Right? And that's interesting. Now think about it. Hopefully you've slid some heavy things, right? Pushed on some boxes or something. So if you're pushing on a heavy box, you want to slide it across the floor, is it harder to get it going, or is it harder to keep it going once you've got it sliding? Hopefully you're all saying to yourself, well, it's harder to get it going, right? You push really hard to get it moving, but then once you get it moving, it's easier. Well, that's what this is showing experimentally, right? The maximum amount of static friction you have to overcome before you get it moving is greater than the kinetic friction. Okay, the technical reason for it, as best answer I can give you, is has something to do with the amount of energy it takes to break the bonds, and if you're already moving, you already have some energy and that kind of thing, but it gets kind of complex. Friction is, at its core, what it is a fairly complex thing. And like I said, one thing that you have to be careful of in your pivots when going through these is that the scaling on the force axis is going to change depending on the trial. And you have to estimate. Okay, you don't have to get exactly what I got, because mine are estimations, and I might be off by a tenth here or there, right? But hopefully you get a slope on your graph that's in the ballpark of mine, right? And you get a shape to your graph that, you know, is predictable, that looks like mine. If you're having a really hard time getting good data, all right, you can't seem to get data that leads to the right thing, I do have a key, right, on the schedule doc, and you can look it up. But I would ask you not to use the key unless you absolutely have to, right, for that kind of thing. I'd like you to do the lab, basically, right? There's a bunch of multiple choice questions to answer first before you get to the actual lab portion, where they're just trying to make you think about what you're having to do and how to do it, okay, as we've done in some other pivots. And then there's a question at the end. The very last multiple choice question is after you've taken data, after you've graphed using graphical analysis, right, and all of that kind of stuff, which is all on your lab sheet. And if you need help with that, there is, of course, always the data analysis with graphical analysis, which is on the schedule doc or linked on the schedule doc. And then it asks you to pick which one matches your slope, right? And if you answer correctly, because your slope was in that ballpark, well, then you're good. You got good data. You can go on, right? If yours doesn't match for some reason, though, that's when you got to go back and check some things. So hopefully this works with the Pivot Interactive. I think it'll work fairly well for you. It's not a great lab. It's a hard lab to do in real life as well as on video, as you can tell. Right? But I think it's good enough to give us a flavor of what's going on here and the relationship between the force of friction and the amount of normal force. And with what we've done in class, we'll be able to tease out what happens with the types of surfaces.